So here last class I was explaining to you the problems are based on torque, parallax theorem and the perpendicular theorem and applications of the moment of inertia. So far we have completed some problems and we continue the problems now also. So now here in the seventh problem what we have taken, it is a disk of a mass capital M and radius R has a concentric hole of radius capital R. So it is not the concentric hole of radius, it is not the capital R, it should be the small r. So that's why it is the small r is here and again its radius is the capital R is here like this, and this is the mass of that remaining portion of this disk is the capital M. Mass of that remaining portion of the disk is the capital M is here, and here this removed part is there, this is the removed part, only this part only has that mass is the capital M is there. And thereafter now you are supposed to find out what is the moment of inertia. What is the moment of inertia about an axis, normal axis passing through the center of the disk and perpendicular to the plane. So that's why this the disk is here and it has a concentric hole here, and this is the axis. That axis is passing through the center of that disk. That axis is passing through the center of that disk and again perpendicular to that plane. So in this case, now how to solve it means, now you are taking an elemental ring, so that is the elemental ring, and of radius, that is it is located at a distance x. So that's why this distance is the x to be taken from the center only, and that is the elemental ring means that's why its a thickness to be taken as the dx is there. Then what we can understand here, this the dx is here. Then what we can understand, there are so many such rings that are occupied in between the small r2 and again the capital R. There are so many such rings, and you are finding the moment of inertia of one of such rings, about this point O, about this normal axis. Then if you are finding that moment, this is the procedure of solving this problem. So if you are finding that moment of inertia of one of such rings about this O, and after that if you are integrating in between the limits, that is the lower to upper limit, then you can find out the moment of inertia of that entire system and with respect to that about the O. Now here first of all we have to find out the moment of inertia of this ring about the O, and for that the problem is here regarding that mass only. So here for the circular ring already we know, for the ring that formula is the that can be taken as the mr square is the formula. Here the problem is finding the mass of that is the ring, and in addition to that we have to find out that distance also. That is as far as the distance is concerned there is no problem at all. So here that distance is the x square only, the problem is with the mass only. How to find out that mass of that ring, and for that what we have to take, it is the pi of capital R square minus a small r square, and its corresponding mass is the capital M. Pi of capital R square minus a small r square, its corresponding mass is the capital M, because it is the overall is the pi r square, and again here it is taken as the small r square, that is in here it is the pi r square is taken, pi capital R square minus a pi small r square, that should be corresponding to that M. Now here that is the area of this disk is the, that can be, area of that is elemental ring is the 2 pi x dx is there, 2 pi x dx, 2 pi x is there, and for that it is the circumference, and after that dx is its thickness, which gives the area of that particular elemental ring, and what is the corresponding mass for that, and we have to take it is the dm is equal to, that is the mass of that elemental ring. So that is the dm is equal to, it is the 2 pi x dx is here by pi of capital R square minus r square is here, and again into capital M. That is the mass. So that's why when you are coming to this moment of inertia of that elemental ring only, that is the di is equal to dm into its distance is the x square, dm into x square is here. So that dm is nothing but it is the 2x, that is 2 pi will be cancelled, so that's why 2mx dx is there, and here it is the capital R square minus a small r square is here. That is the moment of inertia of that elemental ring only, and in addition to that, that is the x square is also there, x square it is a multiplication, it is the di is there, and there are so many such rings are there. There are so many such rings are there which are occupying the space in between the small r to capital R. So that's why if you want to find out the moment of inertia of that entire system, then this is to be integrated in between the limits. So that's why For the total system, it is the integral dA is equal to, and this is taken as the integral 2m by capital R square minus a small r square. It is a constant value. 2m by capital R square minus small r square is a constant. So that's why integral x cube dx is there. Integral x cube dx, and the limits are, you are moving from, this is the from a small r to capital R. So small r should be the lower limit, and again the capital R should be the upper limit. So it is a 2m by capital R square minus small r square integral x cube dx, and again the small r to capital R. Integral dA means this is taken as the I, and 2m by capital R square minus a small r square is here, and this can be taken as the x to the power 4 by 4, and here it is x to the power 4 by 4 as usual, that is a small r to capital R is there. Small r to capital R, and thereafter it is the 2m by capital R square minus a small r square, and here it is the 4 is also here. So we can remove this 2, and this will be the 2 will be here in the denominator. So for the x to the power 4, and what we have to take, it is the capital R to the power 4 minus small r to the power 4. Capital R to the power 4 minus small r to the power 4, and this is nothing but the a square minus b square, and here it is the a minus b is here. So that's why in the numerator, after cancelling in the numerator, it becomes the m by 2 of, and here it will be the r square plus small r square is here. So m by 2 of a capital R square plus a small r square. So that will be the answer. Now once again I tell you. So here what you are given, this is the disk is there, and this is the removed part of the disk. And again here it is the only for the remaining mass only, it is in the m doesn't indicate the mass of the total disk. It indicates the mass of the removed, that is the remaining disk only. And for this portion, this is the m to be taken. Only the problem in this, only that is a smaller difficulty is finding the mass of this ring. Finding the mass of this ring. So that's why now we are taking this ring is there, and we have to find out the mass of that ring, and we are assuming which is at a distance x, and for that what we are taking, that is a pi of capital R square minus small r square. Its corresponding mass is the capital M. Pi of capital R square minus small r square, that indicates this one, and it is the m. And 2 pi x dx, that is the area of this ring. What is its mass? So then it will be. So now it is a dA is equal to, already we know for the ring, it is the mr square about its natural axis. So that's why dA is equal to dm x square is here. When you are applying this dm value here, then on integrating on both sides, then you will be getting that I is equal to, ultimately it is the m by 2 of capital R square plus small r square. So like that. Next one. So it is a simple problem only. Now in this case, it is a straight thin uniform rod of length 4L and mass 4m. So that's why this is the thin uniform rod of mass 4m, and again the 4L is here. Next it is bent into a square. What is the moment of inertia about one side? What is the moment of inertia bent into a square? So then you have to understand, it is not the lamina. It is not the plate or the lamina. So that's why here what is the moment of inertia of that entire frame, square frame, about one of its sides. So about one side means you can take any side. We are taking this side. This side is the axis of rotation. That's why we are giving the arrow like this. And there are 3 bodies are there. That is the 4 sides are here, and 1 can be taken, and 2 is here, and 3 will be here, and again the 4. Now definitely I1 is equal to 0 about this axis. That is the moment of inertia of this side 1 with respect to that given axis of rotation. It will be the 0 because it is not at all maintaining any distance, because of the formula is I is equal to mass into distance square. So it is not at all maintaining any distance. So that's why I1 is equal to 0, and for the I2 and I4 it will be the same. So that's why I2 is equal to I4 is equal to, these are nothing but the uniform thin rod. These are nothing but the uniform thin rod which are rotating about about one end, just like this. So that's why it is a uniform thin rod rotating about one end. So like this. In this case, we already have that formula. It is the ml square by 3. ml square by 3. So that's why it is the mass is the, each mass is the m, and again the L is here. So that's why it is the ml square by 3 is here, and both will be same. I2 is equal to I4 is equal to ml square by 3. Because already you are given 4m 4l, that's why each side becomes the ml. So that's why it is the ml square by 3. When you are coming to this I3 is, and here this is the Now this is the axis is there and this is the I3, this third rod is rotating like this, third side is rotating like this. So that's why to find out the moment of inertia of this one about this axis, just you have to apply the simple formula, general formula is the mass into distance square only. That mass into distance square is the m is here and that distance is nothing but as it is a square, so that's why ml square is here. Now what is the moment of inertia of that entire square frame? What is the moment of inertia of this entire square frame about this given axis? That is nothing but the I is equal to I1 plus I2 plus I3 plus I4 and it becomes the 2 0 and it is I2 plus I4 already we know it is the 2 ml square by 3 and plus ml square is here. So that's why 3 is here and this becomes the 5 ml square by 3. It is a 5 ml square by 3 is there. So that is the 8th problem, is a simple problem, it is not so difficult at all. Here you may get confused as it is the lamina, it is not the lamina. So that's why don't go to the direct formula, it is the m of L square plus b square by 12, don't go to that formula, it is a frame only, it is not the lamina. That's why you have to get that moment of inertia of this frame like this only. Next one is the a thin hollow cylinder. So that is the problem number 9th. In this problem, a thin hollow cylinder is free to rotate about its geometrical axis. And its mass is it has a mass of that is a 6 kg and radius 10 centimeters. A rope is wrapped around the cylinder and what force must be exerted along the rope to produce an angular acceleration of 4 radians per second square. So that's why this is the thin hollow cylinder is there. This is the thin hollow cylinder and in this case that is the rope is wrapped around it like this. And this end of the rope we are applying some force. A thin hollow cylinder is free to rotate about its geometrical axis. About its geometrical axis is nothing but it is the natural axis of that cylinder. So this is the axis of rotation, natural axis of that cylinder and it has a mass 6 kg and its radius is the 10 centimeters. So that's why mass can be taken as the 6 kg and it is the radius is equal to 10 centimeters. So that is the 0.1 meter and thereafter a rope is wrapped around the cylinder. What force must be exerted along the rope to produce an angular acceleration of 4 radians per second square? So it is a 4 radians per second square. Here the simple concept. So in the majority of the problems of that movement, that is the rotatory motion or the rigid body dynamics, here we apply this concept torque is equal to some force into perpendicular distance is one formula. And again torque is equal to I alpha is another formula and majority of the problems are balanced on these two concepts. That's why when you are balancing this force into perpendicular distance to that I alpha, then whatever that question that you are asked to find out, then that will come. So here also now you are supposed to find out the force. What is the force to be applied? Now to produce an angular acceleration, that is the alpha is equal to 4 radians per second square. So naturally when you are pulling it, it will rotate about its natural axis. And to get this angular acceleration of 4 radians per second square, what is the force to be applied? What is the force to be applied means, once again I tell you, it is a torque is equal to force into perpendicular distance. So force into perpendicular distance and thereafter torque is equal to I alpha. Implies that is the force into perpendicular distance is equal to I alpha is here. And that is the F that you are supposed to find out, and perpendicular distance is nothing but, because it is a tangential force, so that's why the perpendicular distance is nothing but the radius only. That radius is the 0.1 meter and here it is the I alpha and that is a hollow cylinder. It is, we are discussing that hollow cylinder. In case of that hollow cylinder, it is nothing but the circular ring in the natural axis. So that's why that hollow cylinder is to be viewed like this. So that's why it is the hollow, that is a circular ring formula, and that formula is nothing but mr square. So that's why it is the mr square should come. Mr square is here and here this is the perpendicular distance, what we can take, it is a capital R is here, and alpha that you are already given, it is the 4. So now we alpha is here. Now we apply the values, that is the F is equal to mr and again the alpha. Now that's all. So that's why m is given that 6 kg and r is the 0.1 and it is the 4 is here. So it becomes the 2.4 newtons. It is the 2.4 newtons. When you are applying this much of force, 2.4 newtons, then only it will produce that of angular acceleration 4 radians per second square. So 4 radians per second square. So that's the problem is completed, and thereafter we are going to this 10th problem. It is a simple problem.